Howdy. This video is on the quantum mechanical description of electrons. If we want to understand how things behave, we have to understand molecules, atoms, and electrons. Now, really small things behave very differently than big things. Electrons, atoms do not behave like apples. To describe the really small things, we need to use quantum mechanics. And so that's what this video is about. After watching this video, you should be able to describe how electron orbitals are solutions to the Schrödinger's equation. You should be able to describe how there are an infinite number of solutions, infinite number of atomic orbitals. Each orbital, each solution, is labeled with a unique set of three quantum numbers, n, l, and m sub l. You should be able to describe how a set of four quantum numbers, n, l, m sub l, m sub s, labels each electron in an atom. And so each electron in an atom has a unique set of four quantum numbers, n, l, m sub l, and m sub s. You should be able to describe what each of the four quantum numbers characterize and the limitations of their values. Given the four quantum numbers, you should be able to determine what kind of orbital it is, and given an orbital, you should be able to determine what the corresponding quantum numbers are. Now, the picture on the left is a very popular, enticing picture of electrons in an atom. It pictures electrons orbiting the nucleus like planets orbiting the sun. It's very beautiful. I kind of think about it as the Simpsons view of the atom. Unfortunately, it's very, 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 very wrong. It's very dangerous to think about electrons in this way. Electrons have wave-like properties. They are not hard spheres. That picture shows them as hard spheres. A better, more accurate way of thinking about electrons is you actually have electron density around the nucleus. It's smeared out. And I mentioned that to understand small things like electrons and atoms, we need to understand a little bit about quantum mechanics. And so quantum mechanics was developed between 1900 and 1925. It was actually developed mathematically in terms of wave equations and in terms of matrices, and a year later it was determined that those two mathematical formulations of quantum mechanics were equivalent. And so Schrödinger developed the wave equation, Heisenberg developed the matrix mechanics. And so Schrödinger had the Schrödinger equation. The solutions to the Schrödinger equation are the wave functions, which are symbolized as capital psi. And so each wave function describes an allowed energy state of an electron. And so you can use Schrödinger's equation to solve the question of where the electrons or what states the electrons can have in an atom. Now, psi doesn't really have a physical meaning. Psi squared is proportional to the electron density of the electron around an atom. Now, you can also think about psi squared as terms of proportional to the probability of finding a given electron at a given point. But again, I think it's better to think about psi squared as being proportional to electron density at a given point. Now, each atom again has an infinite number of orbitals. Only the lowest energy orbitals are actually filled. And so psi squared is proportional to the probability of finding an electron at a given point, or more accurately, psi squared is proportional to electron density at a given point. Now here's that beautiful, enticing, wrong picture again. Again, electrons do not orbit nucleus like planets orbit the sun.
A familiar depiction of the atom shows electrons orbiting the nucleus like planets around the sun. This model is neither accurate nor useful. We no longer think of electrons as orbiting the nucleus, and we cannot predict their location with accuracy. A more useful model is the quantum mechanical view of the atom, which represents the positions of electrons in terms of their probability of being in a particular region around the nucleus. If we could show all positions for an electron with a specific quantized energy, the resulting picture would look something like a cloud.
But again, it's probably more accurate to think about in terms of electron density and not probability. And so I mentioned that each orbital is characterized by a distinct set of three quantum numbers, n, l, m sub l. And so the quantum numbers act as labels for the different orbitals, and again, each orbital has a unique set of these three quantum numbers. Now, n is referred to as the principal quantum number. It labels the shell. And so when we talk about the first shell, we mean n equals 1, second shell, n equals 2. N indicates the relative size, and so the bigger the n, the bigger the orbital. L is called the azimuthal quantum number, also the orbital angular momentum. It labels the subshell, and so what we'll see is that L0 corresponds to S orbital, L1 corresponds to the p subshell. And it kind of indicates the shape. And so L0 corresponds to spherical shape, L1 corresponds to a dumbbell shape. M sub L is the magnetic quantum number. It labels the orbitals of a subshell, and it kind of indicates the orientation. And so L0 corresponds to S, which is spherical. Again, L gives you the shape of the orbital. L equals 1 corresponds to P. L equals 2 corresponds to D, which is the dumbbell shape. L equals 3 gives you an F, which is a little bit more complicated shape. Now, I mentioned that larger n, the larger the orbital. And so when we talk about a 1s orbital, the 1 corresponds to n equals 1. S corresponds to L equals 0. 2s, n equals 2, L equals 0. And 3s, n equals 3, L equals 0. And so bigger n, bigger the orbital. And so the 3s is larger than the 2s, which is larger than the 1s. Now all these orbitals are s orbitals, and so they're all spherical.
The s orbitals are all spherically symmetric. Thus, contour plots connecting points of equal electron density are spheres for all values of the principal quantum number n. When n equals 1, the electron density decreases steadily with increasing distance from the nucleus. When n equals 2, the electron density goes to 0, then rises again to a new maximum. The spherical shell around the nucleus where the electron density is 0 is called a node. When n equals 3, there are 2 radial nodes. In summary, s orbitals of differing major quantum number have the same spherical shape, but differ in overall size and the number of nodal surfaces.
And so it's kind of interesting. If you look at the bottom, it shows size squared, the electron density, as a function of distance from the nucleus. And so if you look at the 2s, first you should notice that the electron density is smeared out. Okay, it's not in any one specific distance from the nucleus, but it's smeared out. And if you look at the 2s, you notice you have a node. And so at the node, there's no probability of having any electron density there. And so one question you could ask yourself is, well, how can the electron go from one part of the orbital to the other part on the other side of the node if there's absolutely no probability of it being at the node? Well, again, electrons are not little particles. They're wave-like properties. And so s orbitals, L equals 0, are spherical. P orbitals, L equals 1, they're dumbbell shaped. And so you can imagine having one along the x, one along the y, and one along the z. When L equals 2, that corresponds to d orbitals, and those are double dumbbell shaped, except for the dz squared, which is a little bit more complex of a structure. And then L equals 3 is a little bit more complex. And so these orbitals all lie on top of each other with the nucleus in the middle. Now this is actually a fairly decent calculation for the orbitals. What you see is that's the 1s, and then the 2s, a 2p, another 2p, and then the third 2p. And again, remember that the electron density is actually smeared out, and so they're not on the surface of those things, but they're actually are smeared out. And so 3 common numbers characterize each orbital in an atom, or each orbital in an atom has a unique set of these 3 common numbers, n, L, and m sub L. Now the possible values are fairly important. N can go from 1 up into infinity. And so again, there's an infinite number of orbitals, infinite number of solutions of Schrödinger's equation. L goes from 0 to n minus 1. And so the possible values of L depend on what shell you're in. Right? So in the first shell, n equals 1, L 0. In the second shell, n equals 2, L can be 0 or 1. M sub L goes from minus L through 0 to plus L. And so when L is 0, that corresponds to S. There's only one S orbital per shell. So, possible per shell. When L equals 1, that corresponds to P. M sub L can be minus 1, 0, or plus 1. And so that's why there's 3 p orbitals per subshell. When L equals 2, that corresponds to D. M sub L can be minus 2, minus 1, 0, 1, and 2. And so that's why there's 5 d orbitals per subshell. And so if we look at the first shell, n equals 1, L can be 0, and so that gives us just the 1s. If we look at second shell, n equals 2. Again, n denotes the shell, and L can be 0 and 1, and so you have a 2s and 2p. In the third shell, n equals 3, L can be 0, 1, and 2, and so you have 3s, 3p, 3d. In the fourth shell, n equals 4, L can be 0, 1, 2, or 3, and so that corresponds to 4s, 4p, 4d, and 4f. And so L goes from 0 to n minus 1. N defines the shell, describes the size. L defines the subshell, describes the shape. And again, please remember L0 is S, L1p, L2d, and L3 is F. And notice that because L goes from 0 to n minus 1, there are no p orbitals in the first shell, and there are no d orbitals in the first or second shell. Now, m sub L goes from minus L through 0 to plus L, and so when L0, when you have the s orbitals, m sub L has to be 0, and so there's only a single s orbital per s subshell. When L equals 1, m sub L can be minus 1, 0, plus 1, and so there's 3 p orbitals per p subshell. When L equals 2, m sub L can be minus 2, minus 1, 0, 1, and 2, and so that gives you 5 d orbitals per d subshell. And when L equals 3, m sub L can be minus 3, minus 2, minus 1, 0, 1, 2, and 3, and so there's 7 f orbitals per f subshell. So we can depict this in a slightly different way. And so on the bottom we have the first shell, we just have the 1s orbital. Then we have the second shell, and so we have the 2s and the 3 2p orbitals. And then the third shell we have a 3s, 3 3p's, and 5 3d's. And so each orbital in an atom has a unique set of 3 quantum numbers n, L, and m sub L. Now, the electrons have a magnetic moment. And when this was discovered, scientists assumed that was because the electron was spinning. You know, macroscopically or classically, sorry, when you have a spinning charge, you would get a magnetic moment. But the electron is not spinning. But unfortunately, this mistake has stayed with us. And so m sub s is the spin quantum number. It denotes the relative orientation of the magnetic moment of the electron relative to a magnetic field. And it can be either plus a half or minus a half. And so it's called the magnetic spin, or m sub s. But again, please remember the electron is not spinning, okay?
Any spinning electric...
The magnetic moment of the electron is purely quantum mechanical in nature. And so m sub s can be plus a half or minus a half. Now, because m sub s has 2 possible values, you can have a maximum of 2 electrons per orbital. And so when L0, that corresponds to the s orbital, m sub L has 1 value, so you have 1 s orbital per subshell, but you can have a maximum of 2 electrons per orbital, and so that gives you 2 s electrons maximum per subshell. But m sub s plus half or minus half, maximum of 2 electrons per orbital, that's the Pauli exclusion principle. And so orbitals have a unique set. Each orbital has a unique set of 3 common numbers, n, L, m sub L. Each electron in an atom has a unique set of 4 quantum numbers, n, L, m sub L, and m sub s. 2 electrons can occupy each orbital. And so 4 common numbers characterize each electron. Each electron in an atom has a unique set of these 4 quantum numbers. And so a question you could see is how many orbitals are in the third shell? Well, third shell means n equals 3. When n equals 3, L can be 0, 1, or 2. And so when L is 0, m sub L is 0, that corresponds to a single 3s orbital. When L equals 1, you have minus 1, 0, and plus 1 for m sub L. That corresponds to 3 3p orbitals. When L equals 2, m sub L can be minus 2, minus 1, 0, 1, and 2. That gives you 5 3d orbitals. And so 5 plus 3 plus 1 gives you 9 orbitals. And so there are a total of 9 orbitals in the third shell. Another question that could be asked is, okay, how many orbitals are in the third shell of sodium? And the answer is exactly the same. All atoms have 9 orbitals in the third shell, but not all these orbitals have to be filled. Okay, so there's a difference between an orbital, or an orbital is a state, it's a room, and electrons. Electrons can occupy the orbitals, but sodium has 9 orbitals in its third shell, but actually only 1 orbital is occupied. And so if we take the n values on the left and L values on top, again, remember n is the shell, And when we talk about the 1s orbital, it means n equals 1, L equals 0. 2p corresponds to n equals 2, L equals 1. 3d means n equals 3, L equals 2. 4f, n equals 4, L equals 3. 5g, n equals 5, L equals 4. And so the number front is the value of n, is the shell. And SPDFG, well, S means L is 0, P means L1, D L2, F L3, and G is L4. And so shells only have surfeit orbitals because the possible values of L depends on n. L goes from 0 up into n minus 1, and that's why in the first shell you only have the 1s. In the second shell you only have the 2s and 2p. In the third shell you only have the 3s, 3p, 3d. You know, all shells with n greater than 1 have p orbitals. All shells with n greater than 2 have d's, and all shells with n greater than 3 have f orbitals. Now m sub L can go from minus L through 0 to plus L, and so that's why there's only one s orbital per s subshell, and 3 p orbitals per p subshell, and 5 d orbitals per d subshell. Now it's kind of interesting. We'll talk about the order of filling in a later video, but in general the order of filling goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. The superscript is the maximum number of electrons in that subshell. And so again, S, you have 1 orbital, 2 electrons per orbital, that gives you the 2. P, you have 3 p orbitals per p subshell, and 2 electrons, so 3 times 2 gives you 6. And D, you have 5 d orbitals per d subshell, 5 times 2 gives you that 10. And we'll see that actually the order filling, the lower the energy orbitals get filled first, the more stable get filled first, and it's based on the electrostatic attraction between the electrons and the nucleus. And so electrons, please remember, are not hard spheres. They're not particles. They have wave-like properties. That electron, it's best to think about in terms of electron density. You have the 1s, the 2s, a 2p, another 2p, and then the third 2p. But we need to understand the electrons if we want to understand atoms and molecules, if we want to understand compounds, and if we want to understand how things behave. I hope that was helpful.